Welcome to section 2.1 of the text Discrete Mathematics and its Applications by Kenneth H. Rosen. This is Dr. Gilbert Eyabi and this is Math 160 Anderson University Discrete Methods. Section 2.1 Learning Objectives. In this section, we would cover definition of sets. We would look at describing sets, the roster method, and the set builder notation. And then we shall look at some important sets in mathematics, the empty set, the universal set, the idea of subsets, and what it means for two sets to be equal, cardinality of sets, tuples, and the Cartesian product. Introduction. Sets are one of the basic building blocks for the types of objects considered in discrete mathematics. They are important for counting, and even programming languages have set operations. Set theory is an important branch of mathematics. Many different systems of axioms have been used to develop set theory, but here we are not going to concern ourselves with formal set of axioms for set theory. We will reserve those when we get to Math 420 and Math 422, Abstract Algebra 1 and Abstract Algebra 2. Here we're dealing with discrete mathematics, so we are interested in a naive set theory. Yet, we will introduce some proofs involving sets. Let's continue with our definition of sets. Definition. A set is an unordered collection of objects. Unordered collection of objects. For example, the students in your class, the chairs in this room, unordered, and it is a collection. And there's one other word which is not here, but I always like to include that word when I define a set, and that is a set is an unordered collection of well-defined objects. And that one word there that's missing is well-defined. The reason is I cannot just say, let A be the set of things. It's not well defined. How do I know what is in the set A and what is not? So it has to be well defined. It has to be clear that X, Y, or Z is an element of a particular set. For example, if I pick the student John, is John in the set students in your class or students in this class? If John is not in that class, then John is not an element of that set. If John is in that class, then John is an element of that set. So it has to be well defined. So the complete definition to me would be a set is an unordered collection of well-defined objects. Now, the objects in a set are called elements. We use lowercase letters to represent elements A, B, C, X, Y, Z. And on the other hand, we use uppercase letters to represent sets. A, B, C, X, Y, Z. So I can talk of the element X in the set X. You see how we write lowercase x and uppercase X? I need you to maintain this definition in mathematics. A set is said to contain its elements. That's obvious. Now, notation. This notation here means A is an element of, and this means element of. So A is an element of the set A. X is an element of the set X. Y is an element of the set Y. And if A is not an element of the set A, we write it in this form. A is not an element of A, and we cross that using a backslash. Okay? So A is an element of A. A is not an element of A. We will see this notation again and again, and we shall use the notation in some proofs in this class. Okay, let's talk about describing a set. We can describe a set using the roster method or the set builder notation. So let's go ahead and start with the roster method. I usually call it the list method. List as in L-I-S-T, because we actually list out all the elements of the set. So I call it the list method because we list everything out, not list as in smallest. Whereas the set builder notation, it's going to be a more general form of describing the set that carries the basic property that each element of the set has to fulfill. We'll see that in just a few minutes. So let's start with the roster method. S is the set A, B, C, D. It actually lists out all the elements of the set. And remember, order is not important. So the set A, B, C, D is the same as the set BCAD, and so on and so forth. As a matter of fact, the set ABCD is the same as the set ABCBCD. So if I put multiple times one element, it doesn't really matter. So all you need to do is just list an element once. The reason is because S is the set that contains these elements, period. So if I were to put A 5 times, it doesn't really change the set. A belongs to that element. A belongs to that set, period. So if I have 5 A's, it doesn't change anything, okay? So as much as possible, we would not list elements twice in a set. So the set A, B, C, B, C, D would simply be listed as A, B, C, D. And there are times we do not want to list out all the elements of a set, so we use ellipses. Ellipses are 3 dots. For example, S is the set A, B, C, D, and I have 3 dots Z. That means it continues in this pattern. And anybody who knows the alphabet knows that it's going to be A, B, C, D, E, F, G, H, right up to Z. So these 3 dots are known as ellipses. For example, if I want to list out the elements of the set S, where S has elements from 1 to 500, it will be 1, 2, 3, 4 ellipses. 500. That means I'm going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, right up to 500. Okay, you do not have to list out all the elements of the set. Using ellipses would convey the idea that you actually would follow the pattern that you're using right up to the last element listed in the set. Let's look at some more examples on the roster method. 1. The set of all vowels in the English alphabet. V would be, you list out all the elements in that set, which would be all vowels in the English alphabet, and that will be A, E, I, O, U, and sometimes Y, but for now there's no Y. The set of all odd positive integers less than 10. The set of all positive integers less than 100. You see, here we cannot list out all the positive integers less than 100. I mean, we can if we want to, but it's not necessary. So what we do is we say S equals the set 1, 2, 3, 3 dots, and 99. I would really prefer not to have so many dots because that destroys the definition of ellipses. So just have 3 dots and then 99. And lastly, the set of all integers less than 0. That is an infinitely large set. So that will be ellipses, -3, -2, -1. Okay, so these all are examples of the roster method. Here are some very important sets in our study of discrete mathematics and in mathematics in general. The first would be the set of natural numbers. Unfortunately, I may have to disagree a little with the textbook. And it's not because I am 100% correct, but because it's an ongoing argument. But I think the general trend is not to consider 0 as a natural number. So the set of natural numbers would actually be 1, 2, 3, 4, 5, 6, 7. When we include 0, we would prefer to call it the set of whole numbers. Okay, so in that case, the set of natural numbers would actually be the same as the set of positive integers. And that is what we would carry in this class. So when we get to proofs by mathematical induction, and I mention the set of positive integers or the set of natural numbers, the understanding is that we are dealing with the same set. It starts from 1 and goes up to infinity. Okay. Then we have the set of integers, which would be the negative integers, the positive integers, and 0. I think I mentioned before that you can actually divide a set of integers into 3 different subsets: negative integers, 0, positive integers. We will come back to that in this class and probably in abstract algebra, advanced calculus, and so on and so forth, because how you split the set of integers is very important when dealing with proofs. And then we have the set of real numbers, which is everything except the set of complex numbers. Then the set of positive real numbers, and the set of complex numbers, which stand as the largest set. Even the set of real numbers is a subset of the set of complex numbers. And then the set of rational numbers. These are numbers that could be written in the form x divided by y, where x and y are integers and y is different from 0. We did define this back in chapter 1. And the set of irrational numbers, which is not listed here, would be the set containing elements like pi, e, square root of 2, square root of 3, square root of 7. As a matter of fact, square root of p, where p is a prime number. All those are irrational numbers. The set of rational numbers union the set of irrational numbers would give you the set of real numbers R. And then the set of real numbers union I, which is the square root of -1, would give you the set of complex numbers. So you can actually build a set inclusion property with all these important sets. Okay, that was the roster method. Let's move over to the set builder notation, which is what you would use in this class and beyond after now. In the set builder notation, you specify the property or properties that all elements must satisfy. We call that the defining property. What is it that all elements in the set must satisfy? That is the defining property of the set. For example, S is the set of all elements X such that, the vertical line means such that. So S is the set of all elements X such that X is a positive integer that is less than 100. So this statement right here, that is the defining property of elements in that set. For example, is 102 an element in S? Ask yourself, is 102 a positive integer that is less than 100? No. So 102 is not an element of S. Is -7 an element of S? Yes, -7 is less than 100, but is it a positive integer that is also less than 100? No. So -7 is not an element of S. Is 15 an element of S? Is it a positive integer? Is it less than 100? Yes, 15 is a positive integer. It's less than 100, so 15 is an element of S. Define the set O to be the set of all elements X such that X is an odd positive integer less than 10. Is 8 an element of this set? Well, 8 is less than 10, but is it an odd positive integer? So 8 is not an element of this set. Now, we can also define O in this form and reduce the writing. The set of all X in Z plus, that means the set of all positive integers such that X is odd and X is less than 10. So if I pick an element, say -7, I cannot even start asking myself, is -7 an element in the set O? Because all elements in O must be positive integers. In addition to being positive integers, the elements must be odd and they must be less than 10. So if you are not even a positive integer, you don't belong to this set. If you're a positive integer, then you have to be both odd and less than 10. At times we may use a predicate, which is actually what this is. S is the set of all X such that P of X. In this case, P of X would mean that X is odd and X is less than 10. Or P of X could mean that X is prime, so we can say prime X. QX, the set of positive rational numbers, would be the set of all real numbers X such that X is in the form P divided by Q for some positive integers P and Q. Both P and Q have to be positive integers. You see that we did not emphasize that Q should not be different from 0, and that is because P and Q are already positive integers and a positive integer cannot be 0. Remember, the set of integers is divided as negative, 0, and positive. So 0 is not positive. 0 is 0. Interval notation. AB is a set of all X such that X is greater than or equal to A, less than or equal to B. We call this a closed interval. The set of all X such that X is greater than or equal to A, less than B. We call this a half open interval or a half closed interval. It's closed at A and open at B. The next set is closed at B and open at A. So this is also a half closed interval, or you might call it a half open interval. And the next set is open at A, open at B. So we call this an open interval. And a little joke, how can you distinguish between an optimistic discrete mathematician and a pessimistic discrete mathematician? Do they call these intervals as half open or half closed? So that is how you know whether a discrete mathematician or a mathematician in general is optimistic or pessimistic. Remember that half full, half empty? Well, mathematicians don't use half full, half empty. We use half closed interval or half open interval depending on whether we are optimistic or pessimistic on that particular day. Let's talk a little bit about universal set and the empty set. The universal set U is the set containing everything currently under consideration. For example, if I'm dealing only with elements from 0 to 10, then my universal set will be the set containing elements from 0 to 10. That is my universal set. Currently under consideration. Everything currently under consideration. Sometimes it's implicit and sometimes it is explicitly stated. If we think there might be some confusion, then we explicitly state what the universal set is. At times, the contents would depend on the context, in which case we don't really have to explicitly state what the universal set would be. Now, the empty set is a set that contains no elements whatsoever. That is the empty set. But it is very, very important. Just like the number 0. 0 is 0, but if 0 did not exist, we would have a lot of problems. 3 minus 3 would be what? So we need 0. So similarly, we need the empty set. And we would use this symbol right here, or we use this to represent the empty set. Do you know what a paradox is? Let's look at Russell's paradox and try to answer this question at the end. Let S be the set of all sets which are not members of themselves. Okay, just think about it. S is the set of all sets which are not members of themselves. A paradox results from trying to answer the question, is S a member of itself? Here is a related paradox. Henry is a barber who shaves all people who do not shave themselves. A paradox results from trying to answer the question, does Henry shave himself? Henry is a barber who shaves all people who do not shave themselves. Would Henry actually shave himself? If he shaves himself, then what happens? He is supposed to be a barber who shaves everyone who do not shave themselves. If he doesn't shave himself, then he belongs to the set of people that Henry shaves. Think about this some more and let's talk about it in class. Or you can answer this on the comment section of YouTube. Wish you the best as you play with Russell's paradox. Here are some things to remember. Sets can actually be elements of other sets. For example, look at this set right here. Its elements are the set 1, 2, 3, A, and the set BC. So the set BC is an element of this set. The element A is an element of this set. The set 1, 2, 3 is an element of this set. As a matter of fact, I could even have a huge, giant set whose elements are the set of natural numbers, the set of integers, the set of rational numbers, and the set of real numbers. That is a set that contains sets, and each of these sets are infinitely large. So this is a huge set. The empty set is different from a set containing the empty set. So right here, this would be the set that contains the empty set. Yes, it's the empty set, and this is the set that contains the empty set, but that is different from the empty set. So this notation is very important, and we have to keep it the way it is. Now let's switch over and talk about set equality. We would revisit set equality. So right now, the definition I'm going to give you, it's okay, but not good enough for the purpose of proofs, but we can use it at least for now. Two sets are equal if and only if they have the same elements. For example, the set 135 is equal to the set 351. And again, if I put multiple of some element in the set, it doesn't make any difference. It's still the same as 135. So we say A and B are equal if and only if for every x. X is in A if and only if x is in B. We would come back to this definition of equality of sets. Before we get to that definition of equality of sets, let's touch subsets, because we would build the definition of equality using subsets, and that is how we would prove that two sets are equal. So the set A is a subset of the set B if and only if whenever X is an element of A, X is also an element of B. So A is a subset of B if and only if for every X in A, X also is an element in B. And that is what we have here. For every element X, X in A implies X is in B. And that is how we prove that A is a subset of B. We say let X be an element of the set A. We then show that X is an element of B. If that happens, then we can conclude that A is a subset of B. Now, very quickly before I move on, if S is an arbitrary set, then it has two trivial subsets. So every set has two trivial subsets. The first is the empty set. The empty set is a subset of every set. So the empty set is a subset of S. And the proof is very easy. A is an element of the empty set is always false. So the empty set is a subset of S. Another way to look at it is, suppose the empty set were not a subset of S. What would that mean? That means there is an element A in the empty set that is not in S. Okay? So remember, A is a subset of B if every element in A is also an element of B. So when would A not be an element of B? A would not be an element of B if I can find an element X in A which is not in B. That is a counterexample, and we shall look at that again in just a few minutes. So if the empty set were not a subset of S, then there exists some element X in the empty set which is not an element of S, but the empty set has no such elements. So we could say that the empty set is a subset of S because we really cannot show that it is not. It's a trivial subset of S. And the second trivial subset of S is S itself. So the empty set and the set S are the two trivial subsets of S. And for any other set, if I pick the set A, the two trivial subsets of A are the empty set and A itself. I just mentioned this a few seconds ago. How do we show that a set is or is not a subset of another set? To show that a set is a subset of another set, we pick an element X in A and prove that X is also an element of B. And to show that X is not a subset of B, we find just one. We find an element X of A which is not in B. And we conclude that A is not a subset of B. And that element is known as a counterexample. Here are some examples. The set of all computer science majors at your school is a subset of all students at your school. Why? If you pick any student who is a computer science major at your school, that student is also a student at your school. So A is a subset of B. The set of integers with squares less than 100 is not a subset of the set of non-negative integers. So that is an example of A not a subset of B, and I want you to find a counter example, a particular example to show that this set is not a subset of the set of non-negative integers. Now let's go back to the equality of sets. How do we prove that A equals B? Now, if we are using the roster method or the list method where all the elements are listed, I can look at set A and set B and determine if A and B are equal or not. But if I'm using the set builder notation, it might be a little tricky to determine whether A and B are equal just by looking at the elements of the sets. So what do? Two sets are equal if and only if they are subsets of each other. So to prove that A equals B, we have to prove the forward inclusion, i.e., we have to prove that A is a subset of B, and then we have to prove the reverse inclusion, i.e., B is a subset of A. So to prove that two sets are equal, we start by saying forward inclusion. Let X be an element of A. And we prove using definitions, theorems, lemmas, axioms that X is also an element of B. And we conclude that therefore A is a subset of B. Then we also say suppose Y is an element of B. And we prove using axioms, lemmas, definitions that Y is also an element of A, and then conclude that B is a subset of A. Then we'll say B a subset of A and A a subset of B implies that A equals B, end of proof. Okay, so two sets are equal if and only if they are subsets of each other. And that's beautiful because even the Bible says it. Jesus says, I am in my Father. He goes further to say, my Father is in me. And then he goes further to actually say, I and my Father are one. Beautiful. There is mathematics in the scriptures. Actually, more than you can even imagine. Maybe sometime I would actually give a lecture on the Bible and mathematics. It's beautiful. Okay, we have looked at subsets, but there is something also known as proper subsets. A set is known to be a proper subset if it is a subset but equality is out of question. For example, the set with elements 1, 2, 3 is a subset of the set of elements from 1 to 10. Equality cannot hold, so that is a proper subset. Okay, so A is a subset of B, but equality does not hold, and therefore we use the notation A, just the subset notation, equality is taken out. So for example, if I'm using Venn diagrams, this is my set A and the bigger one is my set B. So A is a proper subset of the set B and U is our universal set. The box actually represents the universal set because there are some elements in the universal set that may not be in A and may not also be in B. So it's always good to identify what your universal set is when you're dealing with Venn diagrams. And the cardinality of sets. The cardinality of sets or the order of a set is simply the number of elements in the set. If we have it in a roster method, just count. If it's in the set builder notation, it's still possible to count how many elements are in the set using the defining properties of elements in that set. And the notation is the absolute value of A, or at times O, parentheses A, open and closed. So for example, the order or the cardinality of the empty set is 0. It has no elements. The cardinality of the set 1 to 3 is 3. The cardinality of the set that contains the empty set is 1 because the set has one element and the element is the empty set. You see, that is why the empty set is not the same as the set containing the empty set. The set of integers has an infinite cardinality because it goes forever. So a set could be finite or it could be infinite. And then we have the power set. The power set is simply the set of all subsets of a set. We denote that by PA. So look at the set AB. What are all the subsets of this set? Number one, the empty set. Remember, the empty set is a subset of every set. The set containing the singles, we call these singletons. So the empty set containing A, set containing B, and then the set itself. Every set has the two trivial subsets, the empty set and itself. What if A was the set with elements A, B, C? It will be the empty set, the singletons A, B, C, the doubles A, B, A, C, B, C, and so on and so forth. So why don't you try this? Let A be the set with elements 1, 2, 3, 4. Manually find the power set of A. You would observe that if A has n elements, then the power set of A would have 2 raised to the power n elements, i.e. the cardinality of the power set would be 2 to the n. So go ahead and try that with 4 elements and generate the power set of A. And let's talk about tuples. The n tuple ordered, very important. So the n tuples are actually ordered, just like vectors you did in physics. A1, A2, right up to AN. You cannot put A2 first and then A1 next. No, it's actually ordered. The reason is because the way it is defined is important. So let me take you directly to the definition. The Cartesian product of two sets A and B is defined as A cross B equals AB, where A is in A and B is in B. Here is a 2 tuple. So if I had A cross B cross C cross D, it would have been the 4 tuple A, B, C, D, where A is from A, B is from B, C is from C, D is from D. You can see why this is an ordered tuple. Because if I switch this around, this would mean that B is from A and A is from B, and that messes things up completely. Okay, so the n tuple is ordered and it is actually generated from the Cartesian product of sets. It could be 2 sets, 3 sets, 4 sets, n sets. For example, if A is the set with elements A, B, and B is the set with elements 1, 2, 3, then A cross B would be the set of all A, comma B, this two tuple AB, such that A is from A and B is from B. So what would that be? A1, A2, A3, B1, B2, B3. So this will be the set of all elements AB, where A is from A and B is from B. You see, you cannot write A1 as 1A. Order matters. The subset R of the Cartesian product A cross B is called a relation from the set A to the set B. We will talk about relation later in this class, or if we do not have time to get to chapter 9 in abstract algebra, we will deal with relations. So X is related to Y actually means the two tuple XY is in R. It's an element in R. We'll keep that for later. So what if I have A1, A2 right up to AN? I can form the N tuple, which we have seen before, from A1 cross A2 cross AN, and that will be the N tuple A1, A2, AN, where AI is from AI, I from 1 to N. That means A1 is from A1, A2 is from A2, A3 is from A3, and so on and so forth. So why don't you have fun generating for me the three tuples you get from A cross B cross C? How many elements would you get in total? A is 0, 1, B is 1, 2, C is 0, 1, 2. What if I add a fourth and a fifth? Have fun with this. And then lastly, we have the truth sets of quantifiers. Given a predicate P and a domain D, we define the truth set of P to be the set of elements in D for which P of X is true. So the truth set of P of X is denoted by the set of all X in the domain D such that P of X is true. And P of X is just a predicate, so there's really nothing new here. Example, the truth set of P of X, where the domain is the set of all integers, and P of X is the statement the absolute value of X equals 1 would be negative 1 and 1. So we're looking at the set of all X in Z, the set of all integers X, such that the absolute value of X is 1, and the only two values that would satisfy P of X would be negative 1 and 1, and we would call this the truth set of P of X. Okay? It's just a big name for nothing. Basically, what we are doing is we are moving from the set builder notation to the roster method, just listing out the elements that satisfy the elements in this particular set. And that brings us to the end of section 2.1 sets, and we would look at set operations in 2.2, union, intersection, and so on and so forth. Thank you, and God bless you.